I'm the Vice President for South Wales and the West Country with the PWI. I also, at the moment, I'm a Principal Project Engineer and I work with Steve Pearson, who some of you might know, in the Western Wales and Western region team. So what are we going to talk about tonight? So we'll look at some of the flange climbing derailments. We'll look at why flange climbing derailment occurs. We'll look at the way the wheel flange moves along a switch rail, and we'll spend a bit of time looking at how Network Rail controls those risks through the 053 standard, but we won't spend a lot of time looking at the standard. So before we start, how many of you have done 053 switch checks? There's a few of you, yeah. So things to keep in mind. When we're doing the checks with the gauge, and that's quite a lightweight gauge, but what we're really dealing with is a wheel set. So that weighs around a ton. So there's a fair bit of inertia there. And wheel sets really run around on their own. They're normally in a bogey these days, aren't they? So you're now going up to what, 5 tons or something like that, maybe 7 tons for a passenger coach. And obviously for traction motors as well, you've got more of that. So there are considerable inertial and non-track forces in action. For example, bogey rotational stiffness and yaw stiffness and those sort of things. So when you're using the gauge and doing checks on switches, think of, that's what you're really dealing with. That's big, heavy chunks of metal with a lot of inertia and a lot of force. Okay, so the TGP8 gauge we use is basically a thin slice of a wheel. It's the wheel profile of a new P8 wheel profile. And I think by its nature, it's not a simple no-go gauge. So you do need to understand what it's telling you and think about it. Right? So this was born out of when we had a couple of incidents in a row. So we had 2 incidents at Waterloo, and some of you may remember it. Some of you may not, actually, 2006. But we had two derailments in pretty short order, 11th of September, and then another one on the 21st of October on the southern region at Waterloo Station. And the key things that came out of the RABE inquiry is they're both facing point directions, and I'll explain in a little while why facing points are different to using the points in a trailing direction, and indeed why flange climbing derailment on S&C is a significant risk where it's a much lower risk on plain line. Okay, but the other things they talked about were what they described as unplanned maintenance. So this was people reacting on the night to what they found. So the work hadn't been properly scoped up. It was a case of, well, we find this and we'll fix it, or we'll try and fix it. And in both cases at Waterloo, they failed to fix the problem properly. So they fixed the immediate fault but left the switches in an unsafe condition. So in both cases, it was the next train over it that came off. Okay. And these are the 2 sites. So fairly typical high-risk sites. So this is coming in, the train was coming round into the siding. So obviously you've got quite a sharp curve in there because it's a similar flexure where it's almost straight the turnout, but you're going to get hard flange contact on the approach to it. Might as well stay here. This is the other one. The derailment happened back here. Yeah, on the train that was passing round into there. That's the back end of the train. And as you can see, there's quite considerable wear on this switch. So by their definition, they tend to, you need high forces, and high forces usually mean sharp curvature. So facing switch derailments from this cause on a high speed track are extremely unlikely because the forces just aren't there. So having said that they are generally low speed derailments, I think you'll agree, I mean, this is Waterloo, that the consequences could be quite significant. And if you think about the risk of train coming into contact with line side furniture with another train, for example, as well, would be another big risk. Also doing that in front of Waterloo Station is a bit public as well, so it does our reputation absolutely no good at all. So that's really the background of why we started changing the standard and how I got involved into looking in a bit more detail at why we get flange climb derailments. Okay. So we're focusing on here on flange climb derailment. Clearly, there are other reasons in S&C switches. So things like broken switches, point machines moving under trains and that we're not really looking at. We're looking at the risk of flange climbing derailment. Okay. So in 1908, a guy called Nadal, I don't think he was a tennis player, but he may have, came up with this simple equation for the critical value of Y over Q based on this simple analogy of a block sliding up a plane. So Y is the lateral force, so that's the force from the wheel flange outwards. Yeah. Q is the wheel load, which is predominantly the weight of the train, but obviously it's affected by loading and suspension and things like that as well. Beta is the flange contact angle, so that's the angle from a horizontal plane to the face of the switch. Yeah. And then mu is the coefficient of friction between the contact at the contact point on that slope, yeah, and the wheel. So which is obviously affected by the normal force. Okay, so that's the relationship that applies. And what's really important is that at the point where flange climbing derailment's likely to occur, so what we call Y over Q critical equals about 1. So the objective is to keep Y over Q, or the other side of the equation, less than 1, because when you get close to 1, you have a real, your factor of safety is disappearing, you have a real risk of flange climbing derailment. So what we do, so typically we accept it as 1. Clearly, in reality, we want a factor of safety. In essence, we usually work to point, so we'll work into a smaller value, 0.8. Yeah. So I think that's fairly straightforward. So what's going to happen when we start changing these things? So this is the wheel contact area. So we've got Q bearing down on the weight of the train. We've got Y, which is the lateral force. This is the switch. Yeah, so we'll have a normal force in there. And this angle is beta, which is the plane of the two stock rails. Yeah. Okay. So you can see by when we look at this, if we increase B, yeah, we reduce the risk of derailment. Yeah. So the steeper the slope, the less chance of the wheel climbing it. And I think that's fairly intuitive, isn't it? Also, if we increase mu, i.e. we make the slope more slippery, then again, it's going to help avoid a train climbing. We'll look at the mechanism actually in a minute. So again, so from a maintenance engineer's point of view, those are the things we can manage, aren't they? We can manage the lubrication on the switches, and we can manage the flange contact angle by inspecting it and applying rectification. Clearly, we can't have a particularly big influence on Y over Q. That's more the train space, but we'll see how changing that can also cause problems for track. So the opposite side of that, if we go on, is anything which is, so if we increase the risk of derailment, so by reducing Q, so anything which causes wheel unloading, yeah, will increase the risk of flange climb, because obviously we change the product, yeah. Likewise, anything which increases the lateral force, yeah, and we'll talk about what those things are, also increases the risk of derailment, yeah. So we need to be cognizant of the general track geometry as well when we're thinking about the risk of flange climbing derailment at switches. Okay. So where does these figures come from? Well, they came from some UIC research. The UIC published a code 716R called Maximum Permissible Wear Profiles from Switches, and that's what British Rail Research used when the first edition of 053R switch wear management standard came out. And that was based on a lot of observations and some experiments. And they basically said that to have a reasonable ratio of vertical to lateral force, it should be in the order of 0.8 for S&C. That gives you a reasonable factor of safety. And if you put that back into the equation and work it through, that's equivalent to a flange contact angle of 60 degrees for a coefficient of friction of 0.4 and a flange contact of 55 degrees for a coefficient of 0.3. And those of you who are familiar with 053 will be familiar with this 60. It's the intervention point. That's the angle we start to plan to do some work. We must do it before it gets to 55, or that's getting into block the line territory. And when we grind it back, we had a while we just ground it back to 60, but clearly if you grind it back to 60, the next time you come along, you're going to fail it again. So we try and grind to a slightly steeper angle of 65 degrees, which is actually still flatter than the original machining of the switches. Okay, does that all make sense? So think about some other things which affect it. So in an ideal situation, with a single wheel set running down a piece of perfectly geometric track, yeah, it will absolutely, the rolling radius difference, because the wheels have a taper on, will mean that the wheels will steer themselves down the middle and there will be no flange contact, yeah. In practice, that doesn't happen because we don't have perfect track. And also in curves, then you want the wheel to shift, don't you? So the wheel steers itself by shifting outwards so that the outer wheel is now running on a very slightly bigger radius than the inner wheel. And it's quite subtle, we're only talking millimetres here. But that tendency of the wheel to shift to correct the rolling rate difference means that you tend to get a bit of gentle movement in the flange, okay? So clearly in a pure situation where the wheels are rolling as a single wheel set, that's the situation. If you now constrain the wheels, so the wheel sets want to sit radially to the curve, but we've now constrained them in a bogie frame or a vehicle frame, haven't we? So they can no longer do that. They are constrained to stay. There's a bit of flexibility there, but not a lot. But if you have a very stiff bogie, which is what we tend to do in a low tonicity, then the tendency is the wheels don't steer particularly well. And we have that happened quite a lot in some modern trains as well, which also leads to more wear. But the upshot is that normally the wheel approaches the switch with some kind of angle of attack on it. And that has an effect on where the contact point is as well. Okay, so visual aid number one. So if you put this as a section through on straight track with no contact, yeah, and you're going to have the situation there where the contact point will then be right under there if there is flange contact at all, and the contact point will on the top. If you imagine the wheel is now at an angle of attack, so this is my rail, yeah, the effect of an angle of attack is to move the contact point forward and upwards. Yeah. Okay, so if we look at that on this section, so there's a wheel looking along the rail with a wheel with an angle of attack. So if we take, so it moves this contact point forward and upwards. So if we took a slice through AA, it would look like that. Yeah. So it's moved the effective contact down the flange. Yeah. The wheel's still resting on the rail back here, of course, but moves the effective contact, so it reduces the flange contact angle. And that's another factor which in switches is an issue for increasing derailment risk. We don't really compensate for that in what we do with switches. We have safety margins built into it. But if you were modelling it, a real switch and a real situation, a real wheel, then you can actually start taking account of things like this using vampire modelling and things like that. Okay, so that's quite important because that does affect the risk of flange climb. Okay, does Does that make sense? Right. So this is a case of a flanged climbing derailment which didn't quite, yeah? So obviously the switch must have been shut at the time, but you can see here where the wheel has climbed onto the head of the rail and it's run along effectively with the switch closed. It's run along the edge of the switch and then dropped back in again. If you ever see anything like that, block the line. But it does happen, and we do get things like that. And you do occasionally see the marks on the face of the switch. You get scuff marks here, where the wheel has climbed up and then dropped back in again. Because as you think about it, as the wheel starts to climb up onto the flange, the rolling relative stiffness is now huge, isn't it? So it's going to tend to steer itself back into the track again. But it is worth remembering, this was an incident at Victoria Station some years ago, and it was spotted by one of the S&T techs who was working on the track in the days when we used to work on the track with trains. Okay. So that's the sort of theory part of it. So now we'll move on to the forces and that they're in action, and then to explain that. So what are the forces in action? So this is a typical modern turnout. Okay, it's seen during relaying, and it's tipping Sodbury's. If anybody's into it, it's probably been underwater recently as well. So it's a modern design turnout. So in normal running, remember what I was saying, the wheel sets tend to steer themselves to be central using the rolling radius difference. So if you're running straight through, as this is set at the moment, you're probably not going to get any flange contact at all. Yeah, you might get a slight flange contact, but very little. But if you've now reversed the point C going into here, at some point, this wheel set running along here is going to come into contact with the switch and be steered onto a new course. And I think in maintenance terms, I can think of lots of places where this switch doesn't last that long, but this switch is the one that was put in when they laid the turnout, because this switch is going to get all the wear, isn't it? Yeah, and that's within a simple straight turnout. Clearly, if you curve up the main line radius, then you actually start to change things again. But the way we do it in the UK is we keep the lead length the same, we keep the crossing angle the same, we keep the offsets the same. So something's got to change, and what changes is the radius. So these two turnouts are identical. Yeah, this one's a similar flexure, and you can see the effect of the curvature here is to tighten up the radius. Yeah, inside the turnout. So similar flexure switches are always much more at risk of facing switch issues, wear and derailment risk. The contraceptors, the opposite is true. So in this case, if you imagine it was straight, it would be curving around there much more. It's had the opposite effect, hasn't it? The mainline curvature was actually flattened the turnout radius. Yeah. So this generally, contraflex switches don't have this problem to the same extent. They do have problems like this one because of the cant on the main line and all those kinds of things, but we'll put them to one side. They're not the risk that similar flexure switches are. So we spend a lot of effort, I think, these days trying to design track layouts without putting more similar flexure turnouts and things in it. Okay. So let's have a look at the forces. So does anybody recognise that diagram? Mr. Steele will. Anybody else? That's the base geometry of a vertical turnout. Okay. So it's a natural angle turnout. So obviously that's your gauge, 1432 in this case. And the design, the turnout curve actually, in theory, in the design, actually makes a true tangent with the high rail, with stock rail. Yeah. Now, it would be lovely to make a switch like that, but what do you think would be the practical limitations if we did that?
A razor sharp switch to
You'd have a razor sharp switch, and it would be very thin and very delicate. Yeah. So it'd be nice to do that, but what we practically do is from the point where the head, this is 70, so that's the rail head width, the point we go there, we add a planing radius, yeah, which is a flatter radius. But what it means is that where they actually, the switch at the wheel switch toe meets the stop, you have now a finite angle. You've an alignment fault effectively, don't you? Yeah. The entry angle to the switch. And the shorter the switches, so A switches are our shortest switches, has the biggest entry angle. Yeah. H switches, G switches have a much, much smaller entry angle. And that's another driver of why we get more problems with short switches than we do with long ones. Yeah. And obviously, if you're talking about TV 9 1/4 and DV 10 3/4, is quite low speed as well, but quite tight curvature. So what happens to our wheel set as it's turning along? So here's our wheel set. As you can see, I'm an expert at computer graphics as well. So it's happily sailing along straight track in this case. So it reaches the switch toe, and at some point just past the toe, this wheel is going to come into contact with the switch, isn't it? Yeah, and it's going to be steered onto a new course. Obviously, the two axles are constrained within a bogie, so they're going to have an effect on one another as well. But eventually, it gets through the switch and it settles down to some kind of steady curving. Yeah, because this is just a plain line curve from the point of view of the wheels and travelling. But obviously, it's quite a tight curve. So if we looked at the forces involved there, straight track would be very low. There was always some steering forces, but they'd be pretty low, because the flanges aren't in contact or anything like that. When you reach this point here, we get a big spike in the steering force. And anybody who's travelled on a train, you're aware of that as you pass through the switches, aren't you? You feel this slight, it's an instantaneous thing, so the suspension, but there is this big peak, because obviously whilst in the train, you're separated from the wheels by two sets of suspension, either the primary and secondary suspension. If you're a wheel, there's none of that. You basically run into this run and then get steered onto a new course. Yeah. So that's what causes the peak in forces. If we go back a moment and think about just go back to the last slide. Now we think about a similar flexure turnout. So the main line's now curved. So what's the effect of curving the main line?
Tightens the turnout radius.
It tightens the turnout radius and it also tightens the switch radius, yeah. The entry angle stays the same, but the radii are now much tighter. But if the main line's curved, and particularly if it's sharply curved, if you think of the pictures of Waterloo, it's quite likely that you will be running in flange contact already before you get to the switch, yeah. So again, we come into the turnout. Let's run through that. So what happens here? So there's our first case. In this case, there'll be already some lateral force because we're in flange contact as we're approaching the switch. We then have a much bigger peak because it's steering further round, yeah. And obviously because this is tightened up, we settle down to a higher curving force in the turnout. Okay, and it is this which drives facing switch derailment, because typically it happens in the first metre and a half of the switch, because you've got this big lateral spike, and as we saw, anything which increases the lateral force increases the risk of derailment. Yeah, other things being equal. Okay, does that make sense? Any questions online? No?
Why don't we, on similar flex switches, why don't we just put 5 or 10 millicamp on the switch?
You could, and it has been done in the past.
Horrible to maintain, but it's
Like challenging maintaining.
Yeah, it is a challenge, but the answer actually really I think is to try and avoid using. We tend to use short switches for the wrong reasons, don't we? So there are places where it's geographically constrained. In the end of Shrewsbury Station, you ain't got much room before the two routes do this, have you? So you're going to end up forcing a lot of S&C in there. So you will end up with A switches in running lines in places like that. Where we don't have to, we should put in really the longest leads, which are economically sensible, shouldn't we? And yet we still put in quite short leads, even though the main line speed. So we use the turnout thing as the size of the lead, but not necessarily. We don't really think about what's running through it of main line speeds, do we?
Do you think there's any like to stop the wheel unloading in facing widths? Why don't we extend the fronts to 3.7?
Well, again, I see no reason why not. Better still get rid of the joint entirely and weld it up.
Yeah, well, weld everything, but like even if we extend it, then
It moves it farther away, yeah. And we've certainly found we're getting less twist than that since we went over to axle counters, because there are no insulated joints there anymore, so we weld it all up. So, right. That all makes sense then. Yeah. So yes, there is things, and good design, I think, can play a big part in this. For example, which hand of switch are you going to put in? So you're going to have left hands, curved right hands, and things like that, which can be really, really useful. And again, frequently doesn't get done, does it? So, and that can improve, and you can model this. So you can test the scenarios. So what other factors influence this thing? So this is the Waterloo derailment switch. So other factors that affect, first of all, is the track geometry. Track geometry in terms of the design. So have we used a short turnout where we could have used something longer? Can we make any improvements to straighten out the main line? Yeah, so it doesn't become a single flexure turnout. It's sitting in straight track with no cant on it and things like that. And as a RAM, I used to be, involved in that discussion at the Form A stage with our renewals contractors about them demonstrating to me that they had optimised the design. And I wasn't always totally convinced of what they told me either, but we had the discussion, and so that's really important. So the next thing is track geometry, and this is faults that have arisen in the track due to traffic and wear and all those sorts of things. And they're influenced by maintenance standards. And there's two ways that. One, what does the maintenance standard tell you must do? But also, what is the attitude of the maintainer in terms of, how quickly am I going to intervene? How am I going to avoid some of these problems? And we'll look at more at this switch in a minute and see where there's some issues there. Well, lubrication's a big one. We've seen how important it is. So rail lubrication's a good thing because it maintains the shape of the rail anyway. So it prevents the switches wearing out so quickly. And it also prevents them changing shape so quickly with wear. So rail lubrication, and it has the added benefit that it does increase the factor of safety in a derailment situation.
Does friction modifiers, do they have more advantage than lubrication service?
But you tend to need both. Yeah, so friction modifiers are certainly a big help in S&C. We're only really using them in a few places now. But yes, because it enables the bogie to steer better, you actually reduce the angle of attack. So yes, they're certainly worth looking at. And we got several places which have got them in, but specifically for that purpose. Yeah, even though we might have originally put it in because of noise, we've noticed it has had beneficial effects on wear. So yeah, top of rail friction modifiers worth thinking about. If I had a criticism of the other installations I've seen, they've gone too far with it. Yeah, so you don't need to coat the entire thing with horrible grey Guernsey paint. It's the bit where the big steering's going on that helps. Okay, and of course the other thing which affects it is rolling stock. defects. So whilst we don't manage that side of it, we rely on the train operators and the train owners to manage that side of the equation. And I can assure you there's just as many railway group standards for thickness of flanges, wheel turning out, roundness and all those sort of things they do. But it is possible to get a derailment set up where the track isn't at an actionable limit and neither is the rolling stock. So that combination can be an issue. It's very, very rarely it's one side or the other. So we talked about wheel unloading as being important. So what sort of things cause wheel unloading?
Dip joints.
Dip joints, yeah. So the twist resulting from dip joints, yeah. And as Andy said, we very conveniently placed the site-made IRJ at the fronts of the switches, about 3 meters from the toe of the switches, yeah. So, yeah, not good. What else causes wheel unloading?
Poor formation and dodgy sleepers, I suppose, couldn't help. So
Yeah, poor top, yeah, through poor formation, yeah. What else? Oh, which actually sadly is too commonly associated with S&C because the ballast is cyclic top. So we again get those through. So that's the track side. So what causes these sort of problems on the rolling stock side? So what causes wheel unloading on trains? No.
Bad load suspension.
Bad loading is definitely one. That's particularly freight, yeah. Suspension faults, did somebody say? Yeah, so suspension faults. So things like broken springs, because obviously if the spring is broken, it's not sharing the load evenly, is it? Vehicles are fitted with, as vehicle frames and things get twisted over time or during manufacturing, they put shims in to correct that. And I can think of one derailment where they'd got shims the wrong way around. So to put shims in and made it twice as bad instead of curing it. So things like frame twist could be a thing. Not so much of a problem these days because we don't have many. We used to run 2-axle wagons. Frame twist used to be a common problem. Yeah. And as somebody said, yeah, poor loading, particularly with freight trains. And we've certainly, again, when we had a 053 derailment at Shrewsbury, and a lot of that was a train that wasn't particularly well loaded. All the coal had been loaded over one side, which certainly didn't help.
Do twist rails cause any unloading? They must do, mustn't they?
If they're there.
At the actual point of twist.
They put them in anymore.
If they're not there, they'll be wrong way around.
It does cause a problem because it causes the gauge fault. So I wouldn't say it necessarily responds to the thing, but certainly a rapid change of gauge is a trigger for RCF and things like that, because the wheel doesn't. The wheel sees as a sudden change in gauge as going into a curve.
Right.
Yeah. So if you move the rail over, and what happens is it will steer and actually crash into the opposite rail and things like that.
So is the less SO53 faults on inclined patterns, or
The ride's better through. Yeah. Certainly, which is why we've gone back to it, isn't it?
Yeah.
With the NR60 Mark II is effectively vertical, but going back to and the NR56 is going to be the same, yeah. So going back to the complication is you add a lot more complication to the components, don't you? Because the base plates and things like that are much more complex. But you will get a better ride through it, yeah. And we've already seen that up in Europe, yeah, because that's all vertical again. The problem that causes where you run, because the running man's right on the edge of the road, isn't it?
Right.
Yeah. Okay. So another very common cause of poor track geometry is poorly fitting track components. So this is the derailment site at Water. This is the derailment switch. Yeah. So the first question I would ask is what hell's a fabricated crossing doing at Waterloo? Yeah. I know why that's there. It's because they broke the crossing that was there and they scratched around in the bushes and found something that would fit. Yeah. It's much too straight, isn't it? for the situation it's sitting in. That is absolutely fine. Yeah, we've got to get the trains running quickly and things like that. But I would advocate keeping a bodge register for things like this to remind you that this is actually a pretty temporary job. We must go back and change it. And you can see the results of that. Again, we have a big misalignment here, don't we? And you can see the rapid build-up of sideway here in the run up to the toes of the switch. You can see it here, look, it just bang, it starts here, and that's going up into the switch. Yeah. And there's a few other things wrong as well. There's some dippy joints. Yeah. This one back here, for example. Yeah, so again, wheel unloading and those sort of things. So when you're doing your 053 inspections, you do need to be cognizant of the general condition of the track as well, and try and avoid. So these are things which, you know, we set up ourselves, don't we? So okay, so we now talk about lateral loading. So what causes high forces in track? Lateral forces. No. What's causing the forces? Curvature is the absolute thing. Yeah, the tighter the curve, because eventually the steering mechanism breaks down because the wheel can't shift enough to correct it. So the flange comes into hard contact, and we've all heard that. So that's that horrible screaming noise you get. It's because the two wheels are fixed on the axle and they now can't both turn at the right speed. So one of them is slipping. Yeah, and that's what that screaming noise is. So anything which tightens the curvature up's bad news. Yeah, and I think we saw the other example there, didn't we? Poor alignment. Yeah. So in that case, we had a very poor joint there, and you could see it was causing wear problems, wasn't it? So rolling stock again, if we think about what's happening there, similar things. So stiff bogies, so the bogie rotational stiffness is really important. So if that's really stiff, again, you will find that you're going to get higher track forces. Yeah, and again, some of the recent derailments, we found that the vehicles involved weren't bad. Sheffield was a good example. It wasn't bad, but one vehicle had much more wear on the wheels on one side than the other because the bogie was quite stiff and things like that. So again, it wasn't really at the actionable limit, but it was getting. So we're reliant on the rolling stock people playing their part in this as well. And the other thing, which is long rigid wheelbase. So we don't have that to the same extent we used to, but Coco locomotives, even some Bobo locomotives have quite a long bogie and they're quite stiff. So some of them, fortunately, are very good, but things like class 47s, class 37s, which are still running around, are really bad. Class 66s, fortunately, aren't, because they have bogie steering in, which helps as well.
What about what are they, the flirts that are running down on your neck of the woods, South Wales?
They're too damn heavy.
Well, they've got what's the power cars, 7.6 metre wheelbase now.
Yeah, but it's rested. It sits over two bogies. It's suspended between two bogies.
So, well, it's still 7.6 metres.
Yeah.
It's really short, isn't it?
Yeah, that's
So
really short.
what effect does that have on it?
We've certainly noticed an upturn in broken push plates in jointed track because they're much heavier. But it's difficult to sort of judge it. In fact, they seem to steer reasonably well. But of course, they've replaced 2-car trains with 4-car trains. So in Russia, they now run 8 instead of 4. And that's doubling the tonnage as well, isn't it? So there's also an element through that as well. But the motor bit with the motor compartment is quite hefty. Yeah.
It's doubling the wheel straps. It's doubling the wheel straps so they're hitting it as well.
So I've talked about lubrication. This is an example. It's a plain line example, but extreme lack of lubrication. And you can see the snow. Yeah, that's fragments of metal ripped out of the surface of the rail. So clearly you're changing the shape of the rail, aren't you? but also what kind of coefficient of friction are you going to generate there? That's a pretty dry contact, isn't it? You've got a rough surface now, so that doesn't help at all. So lubrication is really, really important to maintain safety. So high risk locations, similar flexure turnouts, places with no lubrication, and short switches are the places we need to be aware of from the maintainer's point of view, where we're likely to have problems. Okay, so this is a flange's eye view of a switch. So we talked about the contact points and things like that. So the wheel's going to make contact somewhere in that first metre, metre and a half of the switch. This is an NR60 switch, and that's actually machined sufficiently. The machining deliberately tucks the tile way under the stockwell, so you shouldn't get contact right at the front. If you have, you've got a lot of stockwell wear. But that's what the wheels. Also notice, and I don't know how clear it is on here, that there is a topping on the switch. So the switch ramps down. Yeah, and that's part of the design, because what we're trying to do, if you imagine the wheel running up here, is we've got to transfer the wheel from the stock rail onto the switch rail. Okay, but this is where our discontinuity in the alignment is, and we've seen that's where our peak forces are. So these are the places to be where you're likely to find the problems. So it typically happens close to the toe, where the angle of attack and lateral forces are the greatest. Yeah, where the switch isn't full height, because again, it's easier to, as the switch gets lower, and that's why we have limits on height of switches, we can actually do that. So let's have a look at a derailment. So this is the flange climbing derailment happening. So, okay. Let's go back again. Go back again. So this was a Class 37 locomotive, and on a derailment site in Scotland. And basically, they'd done, it was all marked up, they worked out what happened. Someone said, well, if you try it again, and it did. If you listen to the sound on it, there's lots of people going, whoa, whoa. So, but you can see what happens. The flange, in case the leading flange on the leading axle, so it's a 3-axle bogie, makes contact with the switch. It climbs up, runs on the top of the switch, and then drops between the switch and the stockwell. And obviously, as you carry on up the turnout, the switch, 2 stockwells, so it's now running on 2 stockwells, and the 2 stockwells will do that as you go on up the turnout, and this will run into derailment. So good. So it is as quick as that, yeah. So, all right. So that's the sort of theory part of it. So let's go and have a look at some real cases now. So in 053, we talk about 5 hazards, which are things we need to be looking out for when we're doing inspection, because they represent a risk. So remember what the 5 hazards are. No is a perfectly reasonable answer. So hazard 1 is side-worn stockwell with a little used switch. Hazard 2 is switch and stock both side-worn, and that's probably the most common one that we encounter with derailment risk, particularly where we're doing remedial work on switches, because actually running this out smoothly is a bit of a challenge. Hazard 3 is a head-worn stockwell. We don't see that very often anymore. Tends not to be such a problem, but a typical place to find it will be in track points. Yeah, because obviously nothing ever runs on the switch, does it? Well, hopefully fine. Yeah. So you're going to get this wear. So you do need to lower it down eventually. Switch rail damage. Switch rail damage is directly linked to lipping. And from a maintenance point of view, if we can remove lipping in a timely way, we won't get anywhere near as much switch rail damage, and we'll talk about that in a bit more detail in a minute. And then the final one is a sharp radius to the flange contact angle. So the switch has got a faceted surface or sharp angles on it, and that will engage particularly with newly turned wheels and can lead to some problems. Okay. Right, has everyone heard of the 5 hazards? Yeah. So we'll come back to that. So let's have a look at some examples now. So these are all derailment sites, incidentally, as well. So hazard 1 is the sidewall and stockware with a little used switch. Does anyone remember what the limit on sideware on switches is?
9 mil.
No. Stick on the gauge. That will be 9. No, it's won't be 6 mil or 6 on the gauge. This is already at 5. Yeah, and you can see here the sideware scar is way below the switch, isn't it? So if you imagine there's a gap behind there, and you can see where the wheels been bending the switch toe tip into the flange way, and you can see indeed where the wheel finally hit it and derailed. Yeah. So, okay, so that's a hazard 1 type failure. Again, you need to make sure in your inspections that you do regularly close the switch against the stockwell, because if this was always looked at open, it's quite difficult to judge whether you've got a problem or not. So, and that's the usual reason that people don't pick up on, is we don't inspect them frequently enough. Moving on to hazard 2, and this is probably the worst one because of what it actually happens. So this is the drawing from, this is an extract from 602, the planing of switches, yeah, and it's a cross section to a full depth vertical switch, but full depth and shallow depth are the same anyway from this part of the rail point of view, and it's about 1 metre from the switch toe, so we're right in the wear area. So obviously all the wheels hitting and being steered are going to start to hollow out the switch because they're going to hit in the same sort of range. And the switch itself here by design is nearly 12 mils thick, so it's fairly chunky still. So what I've drawn on there is to show, so I've done an idealised sideware scar. I've just used the P8 profile, and you can see the effect of that is as the switch starts to wear, yeah, not only does it get thinner, yeah, in here, it also gets shallower, yeah. And as we've seen, as you get shallower, you start moving around this curve again, yeah. So you start running a risk of, again, it increases your derailment risk situation. In practice, that shape wouldn't be a pure P8, would it? It would be an amalgam of all the wheels that run over it on a regular basis. So we'd have some trains they were in the workshops last night, they'd have a new P8 profile, others would be at the limit of the wear the other way. Not all vehicles are fitted with P8s, we use P6s and other things, still a few P1s around and things like that. So it is really important, again, to think about what's happening there. Not so much from the point of view of safety, because we put a 6 mil limit on it, so that is drawn at the actual limit of wear that we should, so we should block the facing moves at that point. Yeah, so it's less than you're allowed to go on plain rail. But the problem is what are you going to do about that? So if you decide you're going to rectify this by grinding, yeah, and it's already down here, we're talking about grinding huge chunks off the switch, yeah. So there comes a point where it's just not worth doing, or there comes a point where grinding, you shouldn't do it anymore. We need to actually replace the switches. And one of the last changes we made to say, if you've got a really badly worn switch, if you can make it safe, fine, but you've still got to replace it within 13 weeks.
Did we not do any building up now, Andy?
Hey?
Don't we build a switch?
We do, but building up that is, I mean, the biggest problem is you send the welders out, say, yeah, we need 9 hours, and operation, say, 2 words, one of which is off. Yeah, so it's just not a practical proposition anymore. Lots of countries have stopped repairing switches now. Yeah. Holland has now, France has. They just don't repair them, they just change them. That's just too risky. Okay. So really important thing to think of again when we're looking at a switch to see if we can repair it or do more grinding, because grinding is only controlled wear, isn't it? You need to think about whether there is enough left in it, and certainly things like Princess Street Gardens, the derailment there was very much directly, and Waterloo very much directly, to the fact that people hadn't scoped the work. Nobody had been and looked at it until somebody had failed it. But the first, all the welders got was here's a copy of the form, go and sort it. And that Princess Street Garden, they were given an hour to do that, which included walking over 2 live roads, which is not a particularly good idea either, is it? But so all the rush and tear just leaves you end up there. In the end, they left the track in an unsafe condition. Right. So that's hazard 2. So what does that look like? This is a pretty gruesome looking switch, isn't it? So as you can see, we've got the side wear scar cutting into both the switch and the stock. And what happened there is the wheel path approaching and basically engages with this slope and then climbs up and over the top. So hazard 2, I guess the answer is you don't let the switches go anywhere near that far before you do it. We need to be more proactive in our maintenance of switches. Hazard 3. So this is worn. So the effect of the stock wheel wearing down is to make the switch taller in comparison, isn't it? Yeah. And what happens is eventually the toe of the switch starts to infringe on the space where the flanges, so you start getting contact on the switch tip, yeah, which either results in the switch tip being broken off like this or bent, yeah. So it doesn't happen very frequently, but we've had them in the past.
Just out of interest, what's holding the slide down?
Which one? What's right with it?
Slide chair. What's holding it down?
Nothing. I told you these are all derailments, right? So, yeah. Something horrible's happened to the lock stretching as well, isn't it? But this is a really, really common one. So damage, switch damage. So as I said, as the switch is designed to sit snugly against the stock rail in the chamfer. If you've got lipping starting to develop, particularly on the top of the switch or on the stock rail face into the chamfer, what happens is the switch and stock now come together. Instead of coming snugly together, they come together at a point, and under the load of a train, you start breaking pieces off the switch. I have seen an S&T team knocking them off with a hammer and chisel as well to get the fencing point lock to work. But so as you can see here, we've lost quite big pieces off the stock rail here. We've lost a whole chunk of the switch, haven't we? There's the switch toes down here somewhere, and we've lost a whole strip off the top, and we've got this really sharp edge there. So when that was all, I think, got some pictures of it cleaned up, yeah. So when it was all cleaned up, you can see that there's this piece of metal that's been hanging on at the front there. That's broken off, and basically you've now got a spike, you know, as thing goes with the wheel and the bones come off, and you can see it quite clearly there. So again, it's just letting it get too far. And the final one is switchblade sharp corners. So this is what used to be called the Pac-Man gauge. This is the new version. That's the old version. I couldn't find a picture of anyone using the new one. But again, we don't want a sharp corner on the switch, do we? Because you run the risk of actually, again, the edge cutting into a newly turned wheel and causing a derailment. And one of the things we learned at Shrewsbury was the weld metal, that because you used to only apply this to austenitic manganese steel switches, of which there's still quite a few left, but also when you do welding, the weld material we use to repair switches is much harder than the parent metal. So again, you need to do it after you've done a weld repair to make sure that you've smoothed off that corner and haven't got a sharp edge. Okay, so that's the 5 hazards. Yeah. And we haven't had one of those recently, but you should never say things like that, should you? So this is the table that appears in the standard, and I think this is really, really important. If you were involved in track inspection, I used to have a small version laminated and in my notebook, because you don't need gauges or anything to actually start looking at these things. Yeah. But obviously, those are the things which are starting to increase the risk. So I won't go through them in detail, but it is well worth, if you do inspections, just to have that with you. Yeah. Right. So the gauges help you quantify the risk, how bad it is. But your first step is to say, well, does this defect occur at all in the switch? Yeah. So, you know, if there's evidently no wear, then that's hazard eliminated. You know, you can eliminate hazard 1 just by looking at it, can't you? Yeah. There's no side wear scar. There's no risk of a hazard 1, is there? So things like that. So I would get everyone just to remember that. And I certainly try to encourage my track patrollers to actually look at this sort of thing. So we've been a long while without a facing switch. That's dangerous talk, isn't it? Most recent one we had was in May 22 at Coatbridge, Sunnyside Junction. How can anything be called Sunnyside in South Glasgow? But there we are. So here's the junction. It's a fairly typical, so it's a main-to-main crossover and then a turnout onto the branch, and it derailed on the facing points of the main-to-main crossover. It was really unusual because passenger trains don't normally use that route, but they were being used because another route was blocked by some major works in the tunnel. So the passenger trains don't normally go. It's normally freight trains that use this thing. So these are the switches. So point of derailment was in here. Yeah. So this is looking into the switch where the derailment happened. So do you think these are at risk of an 053 failure? Why? Similar factor turnout. Yeah, the turnout radius is 240 odd meters. That's fairly tight. Yeah, the main line radius is 400 meters. So yeah, we're right into that thing. They're D switches, so they're relatively short as well. So now, on the face view of it, this switch doesn't look in bad condition, but for whatever reason, their inspection regime in place failed to pick up that it wasn't. So they were monitoring this switch for side wear because the side wear reading was 7. So it's almost on the point of a band facing boot. But some odd decisions were made at that point. So they cancelled they got the new switch to site, and then they cancelled the job because they couldn't do a tandem lift because the headphones didn't work. So they didn't do the job, but at that stage, I said, well, I would like to have thought, I said, well, I've got now got the track blocks all day, in daylight, a luxury these days, yeah. They could have done a really thorough inspection on the switches and just decided, well, do we need to do any mitigation? And they didn't, basically, and a week later, we had a derailment. So there was all sorts of other issues about people claiming they'd inspected it and not inspected it and all the rest of it. So, but that was the last one we had. So as a result of that, we didn't change the standards at all because technically there wasn't anything to do. What they had failed to do was to carry out the requirements of the standards in a thorough way. And there was lots of issues around access. Around the Glasgow DU had 1 person doing all the facing switches. That's quite a risky strategy because none of us are perfect, are we? And if you start getting into bad habits, who's checking to, to make sure, where's the assurance in that? If there's 2 of you going around and you're swapping around, you're going to have a much bigger chance of picking up anything like that, aren't you? So there was lots of it. I won't go through all that because it's the time. Time is getting on. Okay. So again, talking about what we were doing, what do we think the hazards are the most likely on this set of switches? One's definitely one, yeah, because the majority of the traffic is passenger trains on the through route. So yeah, you would certainly be at risk of one. Yeah. Yeah. So in fact, what they'd happen to, and I'll get onto the diagrams, I'll skip through this. This is a bit of the history of it. But, so this is the actual switch. And it's quite interesting that the switch doesn't look, I mean, it doesn't look that bad, does it? So it's not sitting up particularly well. And they had a lot of trouble finding the derailment marks. It wasn't until we very carefully cleaned the switch off and these red spots have been put on just to show where the derailment mark was. So my belief is perhaps because we were monitoring this for side wear, that was all they were checking and they hadn't kept an eye on the switch angle. So when you look at this is the comparison of the actual switch. So this is the dotted line is a new switch profile from the standard drawing, and this is the one on site. And as you can see, it's got very considerable wear on it, hasn't it? We've lost a good 5 millimeters off the head there, yeah, and the switch is quite low as well. So, so blue's at 500 millimeters back and the red's at a metre back. Okay.
On that previous slide, Andy, what's going on with the switch tip? On the previous slide. On your previous slide. What's going on at the switch tip there? Something right at it.
There's a bit of damage, so yeah. But so it says this was on weekly monitoring for side wear. The switch was I mean, rightly they picked up that the switch is reaching the end of its life and did that. But this is when you actually compare the reading. So the red dotted line is the actual contact point, which you can see is below, well below the 55 line. Okay, yeah, so I think the worst contact was somewhere around 42, something like that. So, okay, so that's with the gauge on. And for whatever reason, they'd actually managed to not to pick that up with the, so this profile is produced using the mini prof program as well, rather than the 053 gauge. Okay, so last little bit, still right for time, I assume. Yeah. So I think there's really a need for some, and we have done this, and I think we need to keep doing it, is upping our game on the maintenance world. And I don't know whether how many of you are familiar with reliability centred maintenance, risk-based maintenance, as Network Rail decides to call it. But basically and this is particularly applicable to things like track assets, where wear is tends to be a predictable wear and things like that tends to be so in the principle of that, so if you choose a function of an asset of the track, that would be to sport and guide trains. So yeah, and this is time. If you've got some point where the failure is first observable, or loss of function, yeah, and you can identify where the point it loses functionality for track, that would be hopefully that functional loss would be speed restriction, wouldn't it, or band defacing moves or something like that. Okay, you can actually estimate this time, and you can set your inspection frequencies to make sure that you pick up the fault in plenty of time from where we're going. So here's an example for a switch rail. So the first signs you're going to see on the switch will be build up of lipping. That'll be the first thing you can do. You can pick it up it's quite small. And can you do something about it when it's quite small? Yeah, some places send the 053 inspector with a battery hand and they just remove some of this stuff, just smooth it off. Yeah, so you can do that. So if you don't do anything, this is how the P2F curve was. If you don't do anything, the next thing we're going to get is we're going to start getting the switch held off the stock by the lipping, aren't we? Possibly affects the points operation, hence the S&T get in with an hammer and chisel and take it off for you. Yeah. If you still don't do anything, you're getting down to an intervention limit repair. So we've now got to go and repair it in 7 days or something like that. And clearly that's really bad news for maintenance, isn't it? Because as soon as you start getting into reactive work like that, the first thing that you lose is your planned work, isn't it? So then you might get into a bigger, intervention limit, so that may require a speed or whatever, or blocked facing moves, yeah. And that's when it's failed. We've lost the functionality of the ability to support and guide trains because we've now stopped the trains, haven't we? So I think the challenge is the tendency these days is we tend to operate down here. We've allowed the minimum level. The standard track standards are not a target. Track standards are a minimum. Yeah. So the reason they're there is because it's saying effectively once you get here, you've really got to do something now because we're in, here there be dragons, So we've got to do something. But is there any reason why we can't intervene up here? So an example has been rail management in Wales, where we've been doing this kind of approach for a long time. It takes time to do it, but we've got to the point now where we've shifted our defects in the work bank from up this corner where there were lots of short-term defects down to here now, where the majority of the defects in the database are either 6 months or a year. So it's much more flexibility to plan it. You're much further away from point B if you're operating up here, aren't you? So even if it goes wrong, you've still got time to redo it before you get down there. Yeah. So we need to have, as maintainers, I think we need to really recognise that, as ever, the clever bit is getting from where we are now to the broad sunlit uplands here. And I think we're certainly trying to encourage the track maintenance engineers at the front line now to have their own strategies. This is where we are, and it's problematic for whatever reason. This is where I'd like to be. So how do we get from one to the other? And there can be lots of things you can do there, can't you? So this can have an injection of capital money. You can just not tolerate big defects. We started our one by saying making visible defects actionable, and we acted on all the 3 M's. So we had no 3 M's. And this year, Cardiff is now they now have a personal section target of having less than 250 defects in track now, which is an enormous achievement. It's taken them a long time, but we didn't put a lot of extra resource into it, because when you're dealing with defects up here, grinding the lipping off, how long does that take? That's one man with a grinding machine, isn't it? Either a rail mounted one if it's on the running face, or it's a hand grinder on the back. How long does it take if we get a broken band facing moves? Just the physical cost of having to change a switch in an emergency situation, let alone the penalties we pay for the disruption that it causes. So I think there's a good case for trying to up our game in maintenance. So to summarise, so the risk of flange climbing derailment can be controlled by managing the track geometry to minimise wheel unloading, and we've seen things like twist and top fault. We can manage track geometry to minimise the lateral force, so that's having good alignment, using the longest switches we can have and things like that. We have the correct contact angle on the switch, so the steeper the better. The plane of the switch is the angle measured down, so the steeper that it is, the better. The design's around 72 degrees, but we try to grind back to at least 65 to give you a bit more breathing space. And finally is lubrication. And as we sell Mu, if we can keep the switch slippery, it helps again to guard against derailments. And I think you'd agree that they're all things that are well within the gift of fact, that's what the maintenance organisation is there for, is to deal with those kinds of things. So the final message, I guess, is using the TGP gauge to visualise what's happened. Remember, right at the beginning, I said, think of, you're dealing with wheels, railway wheels. It's a big, heavy thing. Wheels in bogies and the effect that has. So use that to visualise what's happening when you see faults in the switch. Don't just blindly apply the gauges and hope for the best. Okay. And then early intervention just makes a lot of sense in my book, but there we are. That's it. Any questions?
Brilliant. We've not had any questions in the chat then. If you're on the call and you want to ask Andy a question, please feel free to put it in the chat or raise your hand. Likewise, anyone in the room, if you want to maybe raise your hands, and I'm sure we can.
What are the switches machined? I know you say from about 5 degrees.
The machine to about 72, 1 in 4, about 72 degrees. So you are comfortably within the range, and most people machine their switches at similar angles as well, wherever railway administration, because you think about it, it needs to match the it needs to match the wheel profile to a certain extent. So so the reason for 60 is the intervention point, but the idea is if we grind back to 65, you're not immediately going to fail it again. But the key thing is scoping that, because to grind back to 65 can be a lot of work. Yeah, and if you think, what are you doing? All you're doing is ripping more bits off the switch, aren't you? Mm-hmm. So things like damage, you want to repair that really quickly as well. So if you've got a little piece missing, it's maybe half an hour's job just to weld it up and reprofile it so it's smooth again. If you wait till it's loads of bits broken off again.
Going back to what you said earlier, isn't it? It's bigger and bigger and more work.
Yeah.
On the time.
Yeah, and then you get all the risk of not finishing it on time and things like that. Because the one thing about switch repair is once you've started, you've got to finish it, because that's what causes derailments if you don't do that. And all the recent derailments, the Waterloos, Princess Street Garden, Glasgow Exhibition Centre, were all associated with work which hadn't properly been completed. In the run out from where they'd done the grinding, they left a place where there was low flow, low contact angle.
Do we reduce the inspection period on high risk?
Mm-hmm.
Do we reduce the inspection period on high risk?
We do, yeah. So we use risk-based form now, and you put all the track category, tonnage, number of times you've had to repair it, and all this stuff in, and it comes out with a frequency, and that can be between 8 weekly, or you can, the other end of the scale is it defaults to supervisor's inspection frequency. So clearly what we don't want to do is we don't want to spend, if you've got an engineering crossover little used out in the sticks somewhere, you don't want to spend the same effort on it as the S&C at Crewe North, do you? Because that's not where the risk lies. So it allows us to do that. And we've done that with crossings as well now. So again, we have a thing where you input the figures and it tells you what your cross inspection frequency should be. Yeah.
So it's not blindly every 6 months anymore.
No. And that can again be down to 4 weeks.
A couple of questions from the call. So Stuart has asked, are you able to provide any guidance on preferences of going over long similar flexure curve versus slower switch on the straight?
Well, again, it's the flatter. It's as simple as trying to design around the flattest, the longest switch you can use in it, because you increase the rate, you increase the entry angle by using a longer switch. You can model it, so you can. So if you've got all that out design, you can get our vehicle track dynamics people can model it. A lot of contractors, a lot of consultants can do it as well, and they will tell you which is the what sort of damage you're going to get on that switch. Yeah,
but it's a vicious circle, isn't it? Because to lengthen the switch, you're probably going to affect the signalling.
Oh, yeah.
You affect the signalling, you're going to cost yourself a lot more money.
Hmm.
And again, now it's a balance between capex versus opex, isn't it?
Yeah, it's always a balance. Yeah, it is always a balance. But you know, when we get schemes like London Bridge, that was a once in a generation opportunity to actually move things around and improve things. And we must take those opportunities when we have them, mustn't we? So, because it's going to be a long time before we do it again, isn't it?
Got one from Joshua on the chat as well, asking, can you explain why they removed the check for running edge slipping from the inspection form? I feel that this defect, as you have rightly mentioned, leads to breaking out damage to the switch rail, which quickly leads to a short timescale defect.
I don't know why it's gone off the phone. That's a surprise to me. I will look. Okay, so thank you for that. Yes.
We've got one from Richard as well, saying, do you have any view on the potential impact of running HS2 trains on a conventional network?
Oof.
Not sure what speed was settled on for HS2, but I assume they will have a lower conicity and stiffer more to control the wheel set.
Yes, so potentially it's like the high-speed trains that run on the HS1. So we have the high-speed trains, but we also have our own domestic trains that run over it. And obviously they need to be designed to be stable at 140 mile an hour, which is their maximum speed. So the tendency is you end up with quite a stiff train, which doesn't necessarily behave well. You only got to ride into St Pancras on a Eurostar, haven't you? It screams its way around the curve. So yes, there will be implications for that. Yeah, and certainly when we ran them for a short while up to Leeds, Eurostar sets, we had some problems with them. Things have moved on a bit because we do have variable bushing now we can use, but again, that's an engagement we need to have with people. I don't think what it's called now, hall bush. So the bush that fits in the radial arm of the bogie. Basically, it's designed so it's got a small hole and it's liquid filled. Yeah. So if you are affecting it at high frequency, it becomes very stiff because the fluid can't flow. If you start using pretty low frequency vibration through it, then it does allow the fluid to move and the bush gets softer. And that's been quite successfully tried out in quite a few places now. So those sort of things are the things you need to look at to that. But potentially, yeah, you're going to get more wear. So.
Did anyone else in the room have anything? Questions? I don't think we've got any more in the chat, so I'll hand over to Les.
Yeah. Just before I do the vote of thanks, I'll just mention, Pete, you said at the beginning that the February meeting slot is empty at the moment. However, in March, I believe we've got Steve Mucklestone from Railcare Group talking about the rail back for us. So that'll be really interesting. Right, okay, I'm Les Fox, Andy. I'm the co-chair for this section. So I'll just start by saying how appropriate your talk is, particularly for us on the back row here. We're all from Central Rail System Design Team.
Right, okay.
And derailment and sort of S&C inspections and that kind of thing, it's not really our main bag, but these days we are doing a hell of a lot of S&C inspections relating to POE conversions and life extensions.
Right.
Set 3255 reports. So everything you said tonight is really important information for us to appreciate. So I do like your top tip as well about the telltale signs, the 5 derailment risk switches. We are actually out this weekend and next weekend continuing with our S&C inspections. So I'll be taking a copy of that with us.
Okay.
So yeah, I think, yeah, so I personally, I've brought away a lot from this talk, and like I say, it's been really appropriate, and I'm sure other members who joined the talk will feel similar as well. And believe it or not, this is quite a good very good turnout in person for this section, and I think again that just shows how appropriate the talk is for the 50% of the audience who are appropriate.
Good.
Yeah, so Yeah, thanks very much for giving up your valuable time for coming to talk to us. Have you come a long way to do?
I thought about the Gaveni, so it's a couple of hours away.
Then, yes.
Yeah, so.
Yeah.
Yeah, but there's plenty of trains back, and if anyone's going for a pint, I'll happily join you as well.
So we really appreciate giving up your valuable time, and I'll just ask the people in the room to give you a quick round of applause to show our appreciation.
Thank you very much.
Brilliant. We'll draw the meeting to a close, and I see you've got a lot of virtual applause as well on the call.
Good,
So
good. Well, that's always
thanks
good.
for attending, everyone on the call, and we'll look forward to seeing you in February. Thanks, guys. See you later.
Thank you.
We had 25 on the call, haven't we? So yeah, 35. I think it's probably a section record. There and thereabouts.
Yeah, so I've been back on the road quite a lot lately. I've been to Carlisle. Well, it was a bit of an epic trip. Not least, which could be a biblical rain as well. I was there as well. So.
Flooding.
There was flooding, yeah. I was quite late getting there, and I was much later getting home as well. I stayed overnight there because you can't get back in. Obviously, at the same.
We'll find out. In the hotel up at the station.
Hey?
In the hotel up at
Yeah, I stayed in there, yeah.
Yeah, all I tend to get when I'm. Yeah, this weekend.
I'm on test this weekend, so I'm doing STC inspection at the Coventry Panel Gas Siding site. I ordered one after the WDU, should be reballasting.
See, the simple line to refurbs. I'm going to do through this weekend.
Yeah, no, it's like they,
I hope that in the scope we give you, it's all going to be fixed up.
I don't know about.
The reballast site, so just because we're going to be rebalanced, they just need the line to the back to. So what we'll do is do a tech inspection and the designers need to just do the.
Are they all 10 then? Or all your reballasting sites 10?
Most of them are, there's a few concretes, but generally the concrete layouts we've been looking at. I think you say, yeah, that's the where it came from.
That's the end of your car.
But the concrete ones have an addition.
Might be off that actually. Yeah, I think it's off the top.
Yeah, most of them.
Been burning
Not to learn not to touch. So let's try and move on and balance.
Yeah. Once it's set up, it's pretty low, right?
They won't do any grinding. They don't want to do any grinding, so anything that's more just specify. Charters. A little bit backwards, but that's the
Right.
You're going to reballast it comfortably. What's all right?
They're all back in again. The whole lot's been
Really?
We still don't have a means of, despite the fact we've been saying for years now that we've got, well, you did your paper, didn't you?
I think the people of 65 to buy another.
Yeah.
You'd actually better concrete doing it with a stubble machine.
Yeah.
You don't want to be in anywhere doing that. That's what.
Yeah, and the other challenge is to hammer. You know, so there's still no.
You need 40, 60, 40, 60. You won't be any higher to the first week.
No, because it's different, because it's putting the compaction in back into it, yeah.
One bit of kit with you is the back in situ, particularly concrete, and Andy Webb's for it. No.
So they've never really,
I've got that, I look at Sarah.
About this sort of in all different ways. You've got to sort of.
That's good.
We need to look at across. You can't. I'm going to laser, but the laser won't get all across.
Give me a message.
no, the laser just tells you where the end of the tube is.
Yeah, you can't. Yeah, how many times? Sorry, the only mistake, we can't even do this because they keep trying to get it slower. Like, you can't.
No,
It's like getting blood out of the stone.
It is hard.
So it's not, we don't have to stop going.
I tend to be in most of the time, because I need to sign in just.
Yeah.
Blade.
No, but the only thing is, they're going to start with it anymore. It's a lot like, about using that set upstairs, don't they?
Yeah, I've seen what
Yeah, so I noticed that quite a bit.
Yeah, it